I'm Paul Knott from the University of Nottingham, and I'm going to talk about designing quantum experiments using an evolutionary algorithm. So just an outline of the talk. I'm going to start by talking about finding quantum states for optical quantum metrology, which was the topic of my PhD. I'm then going to talk about an algorithm that we can use for quantum state engineering that relates to this optical quantum metrology. And then I'm going to give a discussion and talk about future work. So quantum metrology, one of the main tasks is estimating a phase shift to the best precision that you can. Normally, we take a quantum state, psi. We then apply a phase shift to it. And because phase shifts are always relative to something else, we need some sort of reference that the phase shift is relative to. And then we perform a measurement on the state and the reference. And the main goal in quantum metrology is to measure this phase shift to the best precision that you can. And if we take n uncorrelated photons into this phase shift measurement, then the best precision we can get is the shot noise limit. So the precision of the phase shift scales as 1 over the square root of the number of particles that you use to measure the phase. Alternatively, if you can correlate your photons, if you can use entanglement or some other quantum correlations, you can get the Heisenberg limit, where the precision is 1 over the number of particles. So we get this square root improvement. So one way of looking at this square root improvement is that you can increase the precision without having to increase the power of the laser. And this can be useful in lots of situations, such as gravitational wave detection, where they've basically maxed out their power of their lasers. So they want to get a better precision without increasing their lasers. So they can use squeeze states in these gravitational wave detectors to do that. And also potential applications such as measuring a biological sample, where you don't want to just increase the power of your laser. So I'm a theorist, so one really useful tool that I can use to consider different states for quantum metrology is called the quantum Fisher information. So to calculate this, we take our state, psi, we then apply the phase shift with some unitary, u, which depends on the phase shift. And then the question is, what precision can this phase phi be estimated? So to find this, we can differentiate our state with respect to the phase shift. And then we just take this and plug it into this equation called the quantum Fisher information, which is just the overlap of the differentiated state, and then the overlap of the state with the original state, mod squared. So once we've calculated this, then we can put it into what's called the Cramer-Rao bound, which tells us the precision that we can estimate this parameter, phi. And this is bounded below by 1 over mu times the quantum Fisher information. Mu is just the number of repetitions of your experiment. And we've talked about this quantum Fisher information. So you can see from this, say if you fix the number of repetitions, then what we effectively want to do is increase the quantum Fisher information as much as possible. For the main purpose of this talk, don't worry if you didn't follow all that. This is the most important thing. The quantum Fisher information is a very useful figure of merit for a state, because effectively it's a function that all we need is the state, and then we can calculate this metric, this Fisher information, which is just a real number. So one of the main goals of my PhD was searching for different states which have got large quantum Fisher information. So I looked at a big range of states. These are just ones that you can draw and have nice pictures of. But this is a cat state, which is a coherent state alpha, superposition with another coherent state with a different phase. This is a squeezed cat state, where we take the cat state and then we apply a squeezing operator. And then I forgot the equation for this one, but this is a three-headed cat state, it can be called, which is a superposition of 3 different coherent states with 3 different phase shifts. And I tried lots of different states, many of which you can't draw nice pictures, so I didn't include them here. But I came across the same sort of challenges. So often, the best states on paper cannot be made in the laboratory. And I was also interested in finding states that you can make in the lab, that experimentalists can make in the lab. So the converse of this, that the states that are made in the laboratory often have a small quantum Fisher information. So they can make this squeezed cat state in the lab, but actually the squeezed cat state they can make has a small quantum Fisher information. And also our intuition often fails in designing the appropriate experiments to make these states, because it's quite difficult to design an experiment to perfectly make one of these different states. Another thing I noticed that I was actually using like a trial and error sort of process to find these states. So I'd often take a state, manually calculate the quantum Fisher information, and then try and find an experiment to do that. And I do that with lots of different states. So I wondered whether a search algorithm could do a better job than me at designing these experiments to make these different states. So can we search for the best states that can be made in the laboratory? And this was my new sort of research goal that I'm going to talk about in this presentation. So I've introduced the background, which is this optical quantum metrology and finding practical states. I'm now going to introduce an algorithm that we can use for quantum state engineering. So this is now quite a general scheme that you could use to engineer states that could be used for quantum metrology or other purposes. So if we take two different optical states here, this represents two different optical modes, A and B. And then we apply some operators to these different states, and then perform a measurement on one of the two modes, which gives us our final state. So I'm going to talk about these different elements in a second. But I was interested, like I said, in practical things. So I wanted to just consider practical states that you can input into this scheme, and practical operators that you can act on these different states, and then again, practical measurements that can be done. So this sort of engineering scheme is quite general. It can replicate lots of the quantum state engineering optical schemes that are in the literature, such as these different examples. So just to, I'm just going to check the time. Okay. So just to discuss some of these different inputs, operators, and measurements. The squeezed vacuum is one of the common things that can be done in the lab, and this often gives a good precision for quantum metrology. Also, coherent states are useful. That's effectively just a laser, so this is something that you can make in the lab. And then Fock states. Beyond 2-photon Fock states is quite difficult to make, so I wanted to keep this to things that can be done practically. As for the operators that you can do, I'm not going to introduce all of these, but the most important one is the beam splitter, because the beam splitter entangles the two modes together. And generally, what we want to do is entangle the modes together, and when we do the measurement, that often gives us a good state at the end. So this beam split is really important. And then finally, the measurements. So the measurements I was considered a post-selection or heralding measurements, which is where we perform a measurement on this path. When we get the result that we want, we keep the final state. When we don't get the result that we want, we throw away that state. So one example, if we want to herald onto a single photon state, then we can perform a photon number measurement. If we get 0 photons or 2 photons or more than 2, we just throw away that state. But when we get 1 photon in this measurement, then we keep the final state. So this is this heralding or post-selection measurement. This is a nonlinear process that is crucial for making highly non-classical states using this sort of method. And the sort of measurements I considered, again, were practical measurements like quadrature homodyne measurements. This is like an on-off detector where you can either detect nothing or you detect 1 or more photons. This is something that can be done in the lab. And then also photon number resolving detection. So say if we want 2 photons exactly, we need to be able to resolve the number of photons. This is actually the most challenging experimental part. But you can resolve these sort of numbers of photons to a reasonable precision now. So how then do we combine, how do we find optimal input states, operators, and measurements that we can put into this scheme to find the best states for quantum metrology, which is what I was trying to do. So one way is just to systematically sort through all the different combinations and all the different parameters in this toolbox. Now this turns out to be impossible on current computers because there's just too many parameters. We could just randomly combine these elements, so pick a random selection, put it into here, and see what state comes out. This actually turns out to be surprisingly effective, but there must be better ways to do this. So I thought about using an evolutionary algorithm. So this is a natural selection-inspired search algorithm, which I'll introduce next. So if you understand natural selection, you already have a good idea of how evolutionary algorithms work, like this evolution of giraffes with long necks, for example. So we can take potential solutions to a problem. We call this a population of solutions. We can then apply some sort of fitness function. For me, the fitness function was the quantum Fisher information. So the larger the quantum Fisher information, the better. Using this fitness function, we can throw away some of the solutions which were not very good at all. We then take the ones that were good. We can combine some of them together, which is like a breeding phase where you mix different solutions. You can then apply mutations to some of the solutions to make small changes to them. And then again, apply a fitness function. And after lots of iterations of this, you end up with states or solutions which are highly suited for your task. Now, I've introduced this evolutionary algorithm, but actually, when I did this, I programmed this by hand, and my algorithm worked before I actually introduced having populations or this recombination, this breeding. So effectively, it was just like a random hill climbing algorithm where you find a solution, make a small change, see whether that solution is better or worse than the previous one, and you do like a random hill climbing like that. So just to give slightly more detail about how the algorithm works. So we have what we call the DNA, using the terminology from evolution, which is a string of, for us, it was roughly 100 different numbers. Some of them can be binary, some of them can be integers, or they could be real numbers. And then once you have this DNA, then this will describe a specific experiment. So this one, for example, could describe this experiment where you take two different squeeze states, a beam splitter, and then do a 2-photon measurement. Once you've got you can then simulate this experiment, which gives you a final state, and then we can calculate the quantum Fisher information, or in other words, the fitness value of this specific setup. But for the purpose of the algorithm, this really, we can just imagine this as the fitness value is just a function of the DNA. This whole thing is like the way that we do the function. So if we look at the DNA, we just represent this as 2 dimensions, but really this is like 100 dimensions or so of parameters. And then the fitness, we have this fitness landscape with global maxima and local maxima, and we want to try and find the DNA that gives us the best fitness function, so we want to find these peaks. And the evolutionary algorithm, or it turned out in my case just this sort of random hill climbing algorithm, is a good way to find these maxima. So just some examples that the evolutionary algorithm, sorry, I shouldn't say evolutionary algorithm because this was the first iteration, so it wasn't really evolutionary algorithm. But the states found by my original algorithm, one example, the algorithm produces, it gives you this as its output, this sort of form. So it really does give you the experiment that you know how to do. So this one, for example, is 2 squeeze states with 2 different magnitudes and phases, a beam splitter with a transmission probability 15%, and then a 2-photon heralding measurement, which gives us this final state called T1. This is because the algorithm is called tachykoma, which I'll introduce in a minute. But this is T1. I'm just going to introduce this figure because it's going to come up again. So this is the average number of photons in the state, and this is the quantum Fisher information. In metrology, we're also interested in the number of photons in the state. You don't just want a large quantum Fisher information. You want a large quantum Fisher information for a given number of photons. So this gold line is the shot noise limit. This is the best that you can do classically with a classical state. This one, this sort of green line, is the squeezed vacuum state. So this, you can consider this as the best that could be done practically up to date in the lab using a squeezed vacuum. But this is the state T1, which has got, you can see it's got a much improved precision or quantum Fisher information than these different states. But one really interesting thing is that the algorithm gave parameters for these states that are quite unintuitive. So the magnitudes of these different squeeze states are quite different, and the phases, I couldn't find an obvious relation between the phases. It wasn't pi or pi over 2 or something like that. So if I was trying this experiment, I would always try some sort of reasonable integer multiple of pi for the phase shifts. But that didn't happen. And this is the advantage of using these sort of algorithms, that you can get experiments that you didn't really expect to get. Another example, which is called T2, is taking, again, 2 different squeeze vacuums. We then apply a displacement to this state. Again, a beam splitter, and then a 3-photon heralding measurement. Now, the higher the photon number you want to herald, the more difficult it is. So this is a more difficult experiment. But this is the Fisher information of this one. So you can see, again, it's got, I think it's a factor of 6 improvement over the squeeze vacuum. And it's got a 4-fold precision improvement over the shot noise limit. And in quantum metrology, this really is quite a big improvement. I should say this doesn't include when you include photon losses. But in a perfect experiment, this would have a huge improvement. just some more examples. I'm not going to go through these, but some of these are more robust to photon loss. Some of them are easier to produce experimentally because, say, this one involves a homodyne measurement, which is generally easier than a number measurement. And then some of them have this one's got a Fisher information even greater than T2, the one I showed before. But this involves a more difficult heralding measurement. Okay, so I've introduced this algorithm now. I'm going to talk about, give a discussion about this and talk about some future work. How much time do I have?
You have about 15 minutes.
15 minutes? Okay. Okay, I can take my time. It should be 5 minutes maximum, so that's fine. Yep. Okay. So just to compare this to other work in the literature, so my original paper on this was in 2016 in New Journal of Physics. And at the same time, Mario Kren and Anton Zeilinger in Zurich, sorry, not in Zurich, in Vienna, had this paper, Automated Search for New Quantum Experiments. And now the work presented by Alexei Melnikov and also Hans Briegel on this active learning machine to create new quantum experiments, which was presented this week. So we've got the same general idea, which is using algorithms to design new quantum optics experiments. But then some of the differences, so I was using this random hill climbing algorithm, and now we're starting to use a proper evolutionary algorithm, which I'll talk about in a second. And I was interested in states for quantum metrology. Whereas they were originally using like a random search algorithm with some sort of learning, so the algorithm learns from previous experience. And now they're using this reinforcement learning algorithm. And they are interested in entangled states, such as these high-dimensional entangled states. And also the encoding, this is a sort of technical detail, but the encoding is slightly different. They were looking at angular momentum states. But now I've now started a research fellowship funded by the Royal Commission of the Exhibition of 1851. So I've now got 3 years to try and do this on a much bigger scale. So some of the extensions that are currently works in progress. At the moment, I'm working with a PhD student in Nottingham, Rosanna Nichols. One of the first things we're going to do is increase the number of modes of this system. So as a general intuition, the more modes you have means you can get more entanglement between the modes. And then when you do this heralding measurement, you often you herald more interesting, more exotic states. Another thing is that you could see from how I presented this, the fitness function that I applied to this state, which was the quantum Fisher information, you can quite easily change this fitness function and keep the rest of the algorithm the same. So I'm going to look at a much greater range of fitness functions like multi-parameter metrology, which is when you want to measure multiple parameters simultaneously. States for quantum computing, interesting entangled states that might be interesting fundamentally, and then maybe asymmetric entangled states with interesting coherence properties. All these sort of things I'm going to try in the algorithm. Then I'm going to extend the toolbox. This is something else we're currently doing, because these are not all the things that you can do in the lab. There's more things that can be done, so we want to extend that. I'm going to use a proper evolutionary algorithm. Again, we're in the process of doing this at the moment. I'd also like to try this reinforcement learning that Alexei introduced. And then we've got some plans to go beyond optics with some collaborators in MIT and NTT in Japan. I say beyond optics, beyond continuous variable optics. There's linear optics ideas as well. But one of the things we're currently doing is to try and make this even more realistic that you can do in the lab. So this is how I imagine a quantum optics table, because I'm a theorist. It's quite scary. But we're working with experimentalists, in particular Jonathan Matthews and Lana Minay in Bristol, and also Chris Wade and Guillaume Takanda, which I can't remember how you say his last name, in Oxford. And we're looking to model the dominant noise sources that are in their experiments, so we can genuinely use the algorithm to design realistic experiments. And this is, I guess, the ultimate goal of this work, is to take, if you can give me an equipment list of the things that you can do in the lab, and the details of your noise sources, the dominant noise sources in the lab, and then you can say what states or maybe what operations do you want to do with your experiment. We feed this into the algorithm. So this is an artist's impression of the algorithm, Tachikoma. And what the algorithm does is produces an experiment. It produces a design for an experiment. And this experiment can design all these sort of different states, like these cat states, these three-headed cat states, and lots of other things here. And this little thing is quantum Fisher information. So this is the ultimate goal of this work. So just to conclude, by exploiting quantum correlations, we can find these quantum states that give significant precision enhancements over the alternatives. And using this algorithm technique, we can find a selection of practical quantum states for metrology, which have got large precision improvements over the alternatives. And finally, this search algorithm can be modified to engineer quantum states for a wide range of applications. I also need to thank Joe Hollis, who's been working with us to produce some of this artwork that you've seen. And this is just the main paper for this work. And I'd like to thank you for your attention.
You didn't use the extra 5 minutes I gave you.
Questions?
When you say beyond optics, are you also considering to apply this, for example, to deterministic scenarios with other resources, for example, in circuits where you could be given qubits in addition and squeezers and the like, but for example, heralding or probabilistic things are not so applicable?
Yeah, so far we've just considered probabilistic heralding things. We've discussed using deterministic things and whether we can extend this just to quantum circuits in general, but that's something we haven't started yet. Some of the extensions will involve deterministic things, but yeah, so far it's just heralding, just probabilistic.
Sorry, I guess it's in your future plans, but just if you can say a few words. So here your fitness function was the Fisher information.
Yep.
Can you also add, say, robustness to noise or something like this, so it's such that your proposal is kind of more realistic or more useful?
Yes, yeah, definitely. So the work we're doing with these, I'll just go back to, so this is work that's currently in progress. Hopefully in the summer we should have modeled the dominant noise sources in the experiment, and then this will become part of the fitness function will be, well, this is probably a better way of looking at it. If we will include the details of the noise into what we put into the algorithm, we'll say we've got these optical elements that we can use, and we've got this amount of noise. And then the question is, what's the best state you can make given that noise and given those elements? But we can also modify the fitness functions to include things like, say with this experiment where there's a 3-photon heralding measurement, then there's a certain probability that this will succeed. And sometimes the probability is like 1 in a million. So you want to include this probability as part of the fitness function. You might just want to consider experiments that happen with 10% probability, say. So we can modify the fitness function to have multiple different fitness functions. Yeah.
Can I see that picture of the experiment again?
Yeah. Oh, wrong way.
Yeah, I think that beam splitter in the upper left-hand corner is misaligned. Okay, so here.
I think you already said that your future plan is to include also the success rate in your fitness function.
Yep.
But wouldn't it be like the natural way? I mean, you look at the Fisher information and you said the precision also depends on how often I repeat it. So this mu.
Yeah.
And doesn't the success rate directly transformed into some repetition function mu, so that you can just include it into the quantum Fisher information?
Yeah, it's a good question. The way that this works, I don't know if I can. Oh, okay. I thought this would be a clever way to get between slides, but it doesn't work. So, I'll show you the quantum metrology slide. So this is the way you measure the phase shift, is preparing this state and then sending it through the phase shift. With this heralding scheme, we'd only keep states which have got the right heralding. And if you get the wrong heralding measurement, say if you want 2 photons and you get 1 photon, we just wouldn't send that state through the phase shift. We just throw that state away. And the important thing in quantum metrology is what resources you send through the phase shift. So if you don't send it through the phase shift, you don't have to count it as your resources.
But it may
It might make the experiment longer, that's true, yeah. If that's one of the concerns, is you have to do it in a certain time, then yeah, definitely the heralding probability is an important part of it. Yeah, you're right in that case. So I guess maybe you want to measure a biological sample and you have to do it in a certain time period. Yeah. But we can include these as part of the fitness function, so that's, yeah.
More questions? I actually have a question about this. It's actually very similar to the one that Ramon was making. So, you know, when you have this kind of a Heisenberg limited measurement, then there's these generic results that say, in the presence, this 1 over n scaling only will scale up to the point where, you know, decoherence and noise kicks in.
Yep.
Now, you're not at that stage yet, but what would get you to that stage where you cease to be Heisenberg limited and you just go back to the ordinary square root of n?
I guess in terms of practically speaking, the scaling isn't that important. It's more because so the states that we considered have this scaling that I've showed without any loss. Once you include loss, once we include a realistic amount, like 20% loss, say, then the precision reduces dramatically. But one of these states, I've forgotten which one, yeah, this one at the top. This is robust enough to loss. So if you have, say, 10% loss, I think this still gives you an improvement. But then it's like a constant factor improvement, which is something like 5 or say % improvement, I think.
Yeah.
So at that stage, we're just considering the constant factor. And I'm not sure when the scaling breaks down.
No, okay, I guess the n here is the degree of squeezing that you're actually using, so you only get a constant
Yeah.
factor limited by the amount of squeezing.
Yeah. Yep, that's true.
Okay. Other questions? I think clearly people need some coffee. So is there a coffee break? And we'll reconvene here at, what is the official time? At 11 o'clock.